Okay, at this point, I'd like to introduce our next speaker, and that's Jesse Bergkamp. He's going to be talking about the synthesis and electrochemical investigations of cobalt-2 complexes for potential use in energy storage.
All right, happy Wednesday, everyone. Yeah, thank you, Tony. Let me share my screen here. All right, can everyone see this and hear me?
Yes, we're good to go.
Yes. Excellent. All right, well, so I'm going to go ahead and start with my acknowledgement. So thank you to CERC, thank you to Chevron, CSUB, thank you to my colleague, Dr. Li from the physics department. And today we're going to be chatting about cobalt complexes. So cobalt is a relatively cheap and abundant element. These complexes are great for donating electrons and accepting electrons. So they've are really good at sharing, basically. And what we're looking for is potential use in energy storage. So we're going to be looking at battery technology here. So just to kind of start us off, why is this important? How can we use this? So here's a image from satellite, Earth at night. And you can see that humans have done a very good job at creating energy and using it, right? Now, unfortunately, 2/3 of these lights and the electric energy production comes from fossil fuels. And currently right now, the human energy demand is approximately 20 trillion kilowatt hours each year. So over the last decades or so, there's been substantial, research into renewable energy sources. And these include solar, wind, hydroelectric, nuclear. Now, one primary drawback of these types of renewable energies is they are intermittent, depending on weather, depending on the area conditions. Of course, for solar at night, sun doesn't shine. So we need to figure out a way to then store that energy. And moving forward, we need to not only use one resource, but we need a diversity of renewable sources. And that's going to be dependent on the location. So over here, let me change pens. Over here, I have a little figure where if we can convert solar energy, let's say using our photovoltaics that have good efficiencies right now, during the day, we could then store that converted solar energy into a tank, let's say that's on the side of your house, in a battery. And then at night, we can use that. So again, kind of big picture, all of those lights that we see and those 2/3 of energy coming from fossil fuels, well, what's the problem with this? As Top presented with CO2, there is substantial evidence of warming. And we could go on about this for quite a long time, but I've just chosen these couple of figures just to show. Up here in the top left, we can see 4 different independent research groups studying the surface air temperature from 1850 to about 2010. And you can see a steady increase in that trend. You can also just take a look at macro scale issues. We can see the glacier volume is decreasing. We see temperature over land increasing, snow cover decreasing, sea level rising. All of these variables are connected. And this figure over here on the right just shows a global average increase in land and ocean temperature. Dark red is record warmest. So I'll let you be the judge. Is the Earth warming? And so how can we utilize solar energy in a more efficient way? And our research is looking into these redox flow batteries. Let me zoom in. And so I'm going to kind of walk us through, and don't be nervous about the beautiful shapes. These are molecules. Each little bend here is a carbon atom. And we're going to be using these organic type compounds. And just to kind of walk us through this figure, so you'll notice that on the right-hand side, we have a more negative or electron-rich side. On the left-hand side, we have more positive. Right, so we've got electron poor. And this is the fundamental construction of a redox flow battery. So you could imagine that from photovoltaics, you would charge up this side, and you could charge this pool right here that's labeled B. And then at night, you could reverse the current. And what ends up happening is then you have electron flow from the electrode over to the more positive voltage side. And once you have depleted that, the next day, sun comes out, your PV supplies electrons, and you recharge your battery. So that's kind of the guiding principle of this. So for our research, in this box below, example of some of our novel compounds that students in my laboratory have made. And we're looking at these anthraquinones and these cobalt complexes seen in blue. And just to give kind of a literature perspective, some calculations have been done for a anthraquinone derivative, and you can see that they're calculating that at negative 0.8 volts. And typically these cobalt complexes from my lab are positive 0.3 volts. And the important thing is the difference between these voltages is the capacity of your battery. So the further negative you can go and the further positive you can go, the more storage capacity you have. So we set off to synthesize these water-soluble quinones. So a student named Elaine Gonzalez, who's now doing her master's up at Fresno State, she worked out this synthesis seen here. So we started with gallic acid, and we can buy this from a chemical supplier. We do microwave chemistry to then make our starting material, as we've labeled it, number 1. And that was already known in literature, but this particular step here to make compound 2 took quite a bit of trial and error. And we finally figured out the appropriate conditions to then make this polyethylene glycol, or PEG, derivative. And the main reason why we wanted this is we were wanting water-soluble molecules, and we also wanted them to be electron-rich. For the electron-poor compounds, we then had our eyes set on these cobalt complexes, and these are much easier to synthesize. We can buy this ligand, and it's a pretty simple reaction, 30 minutes, 55 degrees, and we can make this cobalt complex. And so far we have about 4 or 5 different cobalt complexes to study. Okay. So some of our synthetic results, here I'm showing a ultraviolet visible spectrum. And you can see in blue is our starting material, compound 1, and in gray we see compound 2. And the main takeaway from this is that the absorption of these compounds have changed. Ultraviolet visible doesn't particularly tell you the exact structure, but it's a good initial, did the reaction change something? And so from there, we took a proton nuclear magnetic resonance spectrum, and this was done on our instrument on campus, our 400 megahertz instrument. And these carbon chains in purple is where we were really looking for a particular signal, and we were wanting to find this triplet over here. And indeed, we saw a triplet on the NMR spectrum. And so that was a very promising sign that we had our peg, or the chain in pink, attached to our quinone. So from there, we then passed these compounds on to Dr. Li's students for electrochemical analysis. And she uses a technique which is cyclic voltammetry. And we'll take a look here at a diagram of the working cell on like how you would actually take these measurements. So we need to figure out what type of electrolyte solution to use. We need to figure out what working electrode and counter electrode is the best for these particular compounds. So Dr. Li's students set out and tried a couple different conditions. So we started off with a glassy carbon working electrode, platinum wire. We tried a couple different solvents, as you can see down here in number 2. This acetonitrile seems to be working best for the anthraquinone, and water seems to be working best with some of the cobalt complexes. And here is a picture of the instrument. And so that is a potentiostat in her lab. Okay. So here are some cyclic voltammograms, and I'm zooming into this one right now as kind of a reference. So I had had some previous CVs ran on a series of cobalt complexes, and you can see from these CVs the average voltage is about 0.35 positive. And some of the preliminary work from TJ and Entor from Dr. Li's research lab on these cobalt complexes, you can see that we're not exactly on target. We need some fine tuning. So we need to figure out which electrodes are going to work better and kind of optimize the setup. One important characteristics of these CVs is this particular shape. And why this shape is so important is it tells us that these molecules are reversible. It tells us that they are good at giving electrons and accepting of electrons. And so that is a major requirement to be a component in a redox flow battery. And here is the initial CV of the anthraquinone. And you can see that we're getting approximately negative 0.2 volts about. And so this is very promising that we've already have two different types of compounds. We've got cobalt mediators and we have quinones. And you can see that we're already pushing some of them more negative and some of them more positive. So this is very promising to continue synthesis of these derivatives. So as I mentioned, some of these problems, right, we noticed that different CVs under the same conditions were giving different results. And so one solution that the students in Dr. Li's lab has come up with is that we need to improve our cleaning of electrodes with a polishing kit. And this specialized kit has arrived at CSUB. We haven't yet used it yet because of the shutdown, but that is definitely going to be utilized in the future. And then also we need to figure out which working electrodes are best for these particular compounds. So we're looking into some platinum microelectrodes, some homemade silicon-based electrodes, as well as these carbon nanotubes. Okay, so the conclusions of basically 3 months or so of work is we have successfully synthesized a new water-soluble quinone. We are currently working on a couple new cobalt complexes as far as figuring out the synthesis. We have fully characterized these molecules using a variety of techniques. We are beginning our cyclic voltammetry studies. We're getting close as far as we can tell that these are reversible. We just need to optimize the working conditions. And so future work is we're going to continue synthesizing quinone derivatives and then passing them to Dr. Li's laboratory, start getting the CV data, and down the road put together kind of a miniature hybrid redox flow battery. Okay, well, thank you. Any questions?
Thank you, Jesse. We have time for one question, and then I'd ask the other questions be put in chat. Carlo has his hand up.
Hi, Jesse. Really interesting talk. My question is, that as a biochemist, anytime I see 3 rings, I'm thinking flavins. And
Yeah.
so have you tried doing any of these experiments with flavin compounds using the nitrogens rather than the carbonyls of a quinone to do your electron transfer?
I have not. That's a good idea. I think right now we were predominantly looking at the quinones based off of this particular paper, this 2016 paper, just to kind of have a comparison. The reason why I was a little bit nervous with the flavins is those lone pair on the nitrogens, you could start to oxidize, reduce those, and the CV data might get a little bit more complex. And so right now we're just wanting to keep it as simple as possible, change just the functional group. So instead of the sulfonato, we're adding the PEG, and then see if we can compare with this paper. But that's a good idea moving forward.
Yeah, I just thought the flavins, because they have that long tail, especially something like the FMN molecule that has that long tail with all those OHs sticking out. Your solubility issues wouldn't be quite as hard as with something that's all carbon, much more greasy.
Yeah, that's a good idea. Thank you.
Mm-hmm.
Okay, thank you very much. Jesse, you've got a question in the chat, so I might ask that you address that as we move along.
Okay. All right, thanks everyone.